Today we'll hear from Hazel about the CAESAR project, which I was just reading a little bit more about the project. It looks like a pretty cool airborne project to look at cold air outbreaks over polar areas. So with that, I'll let you take it away. Hazel is a fourth-year student here at OU who's working with Greg McFarquhar. So looking forward to hearing it.
Thank you so much. Thank you for the introduction. I'm so glad to be here. Thank you for everyone attending my seminar today, both in this classroom and both on the online. Today my topic is dependence of marine boundary layer cloud properties on environmental conditions during cold air outbreaks over the North Atlantic. So we are using the results from CAESAR. So CAESAR is our brand new field camping this early year, and it's aircraft measurements. So, and you can see from the background figure, like we have a very fancy C-130 aircraft. So before we talk more about the CAESAR, let's talk about the cold air outbreaks first. So some of you might see these figures many times, but partly I'm going to show this every year as long as we continue working on the cold air outbreaks. So the cold air outbreaks, we can see the CAO is the extremely cold air origins from the polar region, from the sea ice. It travels to the relatively warm ocean. So when they traverse to the relatively warm ocean, when the cold air above the relatively warm ocean below, it can pick up the moisture and heat from the sea surface. So it has a rapid increase of the surface fluxes of heat and moisture. So it results in loss of like massive boundary layer clouds, as we can see from the satellite figure. So typically we have three types of boundary layer clouds during the CAO. The first kind of is the red region, is called cloud streets. It's aligned with the wind direction. It's more like the cell row structure. As they continue developed, it will convert to the cloud street. The cloud cells is more like overcast stratocumulus. As they continue developed, it will become open. It's like open cells, like in the blue region here. So it's called open cells, like more like the cumulus. So that's one way we can identify CAO from the satellite figure. Another way is most common way is using the M index, which is the potential temperature differences between the sea surface temperature and the well-mixed boundary layer top. So there are some discussions about how we define the well-mixed boundary layer top. So there are several like different studies. They choose different levels. Some people will choose 700, and some people will choose 800 hectopascal. And for the recent research and my previous studies, like for the Arctic region, we choose the 850 hectopascal as the upper layer. So when the M is positive, which means the CAO occurs. Another way, like recently, some research groups, like they use the CAO height to define the cold air outbreaks. So which means the pressure thickness between of the CAO air mass. So there are different ways to define this. So over the last decades, like there are several field campings conducted over the Arctic region as well as the Southern Ocean to sample some these are the field campings which they sampled the CAOs over the open water. So the most recent one, like before the COVID time, is the markers and COMBLE over here. Like you can see occurs here. So the markers and COMBLE. After the COVID, like this year, finally we have a new campaign called CAESAR. So CAESAR, the cold air outbreaks experiment in the subarctic region. So why we care about the CAO and why we choose CAESAR as our using CAESAR's data to study the CAO. So the convective boundary layer clouds are very common over the open water during the CAOs in high latitudes, especially off the Arctic sea ice. And they can impact the Earth's radiative balance, so they must be represented in the models. But the previous observations are very limited. Like we can see from this figure, like for the past decades, we only have this amount of field campings sample the CAOs. So, and also they are in the gray zone, like for the cloud weather and climate models. The gray zone means like for the boundary layer process and the moisture process cannot be parameterized independently. So they are very hard to simulate in models. Also, understanding boundary cloud properties and how they vary for different locations and under different environmental conditions are very important for the models and the cloud process parameterizations. So CAESAR, it provides a very good opportunity for us to study the CAOs. It conducts 8 research flights, like collecting very high quality data during the CAOs. So let's talk more about the CAESAR. So the CAESAR was proposed to examine the cloud structure, like marine boundary cloud structures during the CAOs. So we have the National Science Foundation and NCAR, the National Center of Atmospheric Research, NCAR's C-130 aircraft. So on this aircraft, we have lots of in-situ and remote sensors, including the airborne radars, lidars, aerosol and cloud and probes. The CAESAR started from the end of February to the beginning of April. So during the whole season of the whole field campaign, we have 8 research flights. It flew from between the Sweden all the way to the Arctic sea ice to provide good opportunities to see how the cloud properties vary between on different locations. Like different with COMBLE, which we only have 1 station, and during the COMBLE, most of our clouds are sampled like farther downwind, which are more developed, like more like the open cell. But the CAESAR, we can check the clouds for different regions at different stage, so give us more opportunities. And more importantly, we have like more probes that can have more in-situ measurements. So my study focused on instead of the microphysical, we focus on the thermodynamic first. So we look at the WCR, the Wyoming Cloud Radar, which is W-band, to provide, we can see the vertical profile of the cloud structure. We also look at the LiDAR's data, which is the MARLi, Multi-function Airborne Raman Lidar. So the LiDAR can provide more details, but it attenuates quickly. So the radar, we can see the full structure of the cloud, but the LiDAR can provide more details. So we can see the water vapor, even the aerosols, but it attenuated very quickly. So when the LiDAR is above the cloud top, we can only see the cloud top. And when the LiDAR is below the cloud base, so there's no way we can see above the cloud. And more importantly, we have the dropsondes. We have the airborne vertical atmospheric profiling systems. So during the CAESAR field campaign, we have a total of 116 dropsondes during the field campaign. So on the figure on the left, we have the track of the aircraft, and this shows the different locations, like different colors present different days of measurements. So like we have general, we have 3 full-fledged measurements start from the Kiruna, Sweden, all the way to the sea ice, and we also have some other samples here and like focus on the polar lows over here. So among all these 8 research flights, we choose this one, the RF7, the March 16, because it has the most dropsondes. Like here, you can see the high density of dropsondes along this research flight. So with this brand new data from the brand new field campaign, we have some preliminary results now. As the movie here shows, like for this case, like we have very cold air blows to the relatively warm ocean, and we have a beautiful clouds here, and we have polar lows here. But the polar lows move east-south, and it finally it become dissipating. We choose this case because it's a full-fledged flight aligned well with the cloud streets, and it is also sampled a very cold CAOs. It has most dropsondes 36, and so it provide us a very good opportunity to study how the cloud properties depend on the varying boundary layer structures as it transforms from the north to the south. So on the left is shows the satellite figure, and with the blue lines shows the C-130 air track, and the red dots shows each individual dropsondes. So on the right, I plotted this wind direction and wind speed field plot using the ERI5 data. So we can see the wind directions and the cloud structures aligned well with each other. So we can, like, based on the previous studies, like when the cloud streams, like they align well with wind direction, they have more row structures. But when they are fully developed, they have the cell structure. So here is the closed one, and here is the open one. So based on our satellite figure and the wind direction, we can assume that during this day, most of our samples are cloud streams. That means the row structures here. So in order to study like how the properties of these boundary layer clouds vary under different environmental conditions, we introduce several environment parameters here first. We have the M index, which used to describe how the intensity of the M index of the CAO. So the larger the M, the more intense of the CAO. We also have the lower tropospheric stability, the LTS, which also is the potential temperature differences between the 700 and the surface. We have another parameter is called estimated inversion strength, EIS, which calculated based on the LTS. And we also have another two parameters, which called estimated cloud top entrainment index. So there are two index but calculated based on different methods from different research groups. So the first method, they calculated the ECTI based on the EIS and the specific humidity differences between the surface and 700 hectopascal. Another one, they calculated the CTEI based on the potential temperature differences and the specific humidity differences just above the boundary layer height and below the boundary layer height. So there are two different kinds of calculation. We also look at the low-level jet, and of course, we also look at the boundary layer height. So for this case, we can divide our field into three major regions. So first part is through the polar lows. Another part is from the cloud streams. And the third part is over the sea ice. So here is all the environmental parameters change with time on this day. So first, from look at the M index at the very beginning, near the Kiruna, Sweden, we have a relatively lower M index below 8. And when the aircraft flew through the polar lows, we have the increased M at the very beginning, but decreased rapidly after that. So the M index variation within the polar lows are very complicated. But for the cloud streams region, we can see that generally this interesting is increasing trend. So the closer we to the sea ice, the larger M index we got. So the stronger CAO we have. Over the sea ice, we don't have the M index because the M index is calculated based on the sea surface temperature. So over the sea ice, we don't have the sea surface temperature. For the LTS and the EIS, they have the similar trends. Like over the sea ice, they have very stable air mass here, very large LTS, and very strong estimated inversion strength over the sea ice. But for the cloud top entrainment index here, the first method we have calculated based between the surface and the 700 Pascal. They have very similar trend as the EIS. It shows over the sea ice we have relatively strong dry air entrainment, but over the polar lows it's very relative below 0. That's the one method. But we look at another method here, the figure H here. Is calculated based just above and below the boundary layer height. Over the sea ice, we can see the slightly large the dry air entrainment here. But over the cloud streams and the polar lows, we have either 0 values or negative values, which means the dry air entrainment doesn't have a large value, don't have significant values here. So these two methods shows very different results here. And another interesting thing is from look at the boundary layer height. It varies the large variations of the boundary layer height over the sea ice here and increased all the way with the cloud streams. Within the polar lows, we have several drops, it drops down, the boundary layer height drops down. But I don't know how to explain this, partly due to the polar lows, the meteorology conditions are more complicated. And also, we also look at the low-level jet strength and depth. So over the sea ice, we have more low-level jet strength over the sea ice, but during the cloud streets, we have several points drop some shoes. The low-level jet depths are very deep during the cloud streets. So with all these 36 dropsondes, we can create these kind of figures to show how how the environment parameters change with time as well as height. So these figures shows how the air temperature change over time and height based on the measurements of these 36 dropsondes. So here is very close to the Kiruna, and all the way is over the sea ice. So over the sea ice, we can see the air temperature is very low as the aircraft. So the white dots here shows the average, shows the estimated boundary layer height here, and the red solid line shows the location of the aircraft. So from the sea ice, we have a relatively lower boundary layer height, very cold air temperature. As they move to the more closer to Kiruna, to the land, we have like increase this temperature, especially like when the air masses cross the relatively warm ocean, we can see the temperature increase, as well as the change of the boundary layer height. They are very can see some trends of the boundary layer height very similar to the trend of the temperature here. And similarly, we have the potential temperature profiles. Over the sea ice, we can see the relatively lower potential temperature, and it increased rapidly through height compared to over the polar region, polar region. So we first focus on the cloud streets regions to see like how these clouds vary with each other. So here's like cross-section figures from the radar and the LiDAR. So the first panel shows the radar reflectivity. Different solid lines shows the location of different dropsondes. And the second, we have the Doppler velocity figures here. The green dots here shows the location of the boundary layer height. And for the orange lines here, orange dots here, because we cannot estimate the cloud base using the radar measurements only, and also when the aircraft is above the cloud top, the LiDAR is attenuated very quickly, so they cannot penetrate to all the way to the cloud base. So for the LiDAR depolarization and LiDAR scattering ratio, we can only see the upper part of the clouds. So the one way we estimate the cloud base height, we are using the LCL, the lifting condensation level, to estimate the base of the cloud, the height of cloud base. For the LiDAR's measurements, the depolarization and the LSR, the LiDAR scattering ratio, we can use these two measurements to estimate the cloud top phase. So for example, when the dipole is relatively lower, very small, but we have a relatively large LSR, which means we can have more, it's more like a supercooled liquid water phase at the very cloud top. But for some of the cases, like we have the cloud top, liquid cloud top at the cloud top, but we have ice below the liquid phase. So this kind of situation is very common during the season field camping. So we divided the cloud streets into two zones. So zone 1 in red and zone 2 in blue. So zone 1, they have a higher M index and is very early stage of the CAO. And zone 2, we have a relatively lower M index and is relatively late stage of the CAO. So compared to these two regions, so that's the two regions on the satellite figures here. On the right is the similar figures we see of the air temperature, is the relative humidity respect to ice over time and height based on the measurements from dropsondes. For the zone 1 and zone 2, you can see around like right below the boundary layer height, like the clouds more ice saturated the zone 1 compared to the zone 2. And we got the similar figures like results here. That's the averaged sounding profiles compared to these two regions. So we have the temperature, dew point, potential temperature, relative humidity, virtual temperature, specific humidity. We have horizontal wind speed. So generally, the zone 2 have a little higher like horizontal wind speed and near the surface compared to zone 2. which means that when the air transferred from the big sea ice all the way to the land, like we have like more stronger horizontal wind speed near the surface, for the later stage, and these zones of these boundary clouds, they are decoupled with the surface. And for the zone 1, we have more like ice saturated situation compared to the zone 2, very similar to this figure. The vertical wind speed like is it's harder to like they are quite similar here. And the most important thing we see the boundary layer height for the zone 2 is higher, and the cloud top height is also high. So next we also look at the CFAD. So that's the vertical distribution of the Caesar radar reflectivity on the left, and the Doppler velocity on the middle, and the spectral width on the right, to see how these like different dashed lines shows different percentile confidence interval. And the solid lines here shows the maximum values. So and the horizontal lines shows different boundary layer height, average boundary layer height for different zones. So in general, for the zone 2 later stage of the CAO, they have the higher average boundary layer height, higher cloud top, a relatively large of the radar reflectivity, probably due to like when the CAO developed further downwind, they have more ice crystals developed within the clouds, which probably can cause the large values of the DBZ. But it varies with the cloud boundaries. So the next thing we do is normalize these results. So for the 0 represent the cloud base, the 1 means cloud top. So for the zone 2, for the downwind, we have relatively large DBZ reflectivity, but also have the large positive Doppler velocity, which means more like upward motions. But it's for the zone 2, they have the negative, more negative Doppler velocity, probably have more precipitation compared to the zone 1. And the interesting thing is for the zone 2, they have the relatively large spectral width compared to the zone 2. Compared to the zone 1 is have stronger spectral width compared to the zone 1. So that's all the preliminary results here. So we see we do see some differences between the different zones, different location of these clouds, but now we don't know how what process cause these differences, and which processes are more important. Is the variation of the boundary layer height, like the thermodynamic change of the boundary layer height, can influence the cloud properties, or the microphysical properties within the clouds can lead these kind of changes. So we are not sure at this moment. So further studies are required to investigate these studies. So for the future plans, like the satellite figures we show is on the way out, like we flew from the Kiruna all the way to the sea ice, but on the way back we don't have the dropsondes. So but we can double our samples, like using double our radar and lidar samples when we count the on the way back. And also for because we don't have the dropsonde on the way back, so we can estimate that to create some estimated dropsondes, we can estimate that on the same location when the environment won't change rapidly. So the previous dropsonde at the same location probably can represent the similar vertical structures of the temperature, pressure, such on. So that's the estimate dropsondes here. And more importantly, for the on the way back, we have the flight. We have on the way out, all the aircraft is always stay above the cloud top. But for the on the way back, we have a sawtooth pattern. The flew through the clouds, so we can have more interesting data here. And for also, we have the liquid water path data here from the radiometer. So, but it's upward. So on the way out, we don't have the liquid water path data. But on the way back, when the aircraft flew through the clouds, we have some good measurements of the liquid water path. So from here, we can tell us from some good stories about the precipitation in liquid water paths. And another thing I'm going to do is also include the radiation from from the radiometer. So we can see some very interesting patterns from the radiometer, the downward, upward irradiance, the visible infrared irradiance when the aircraft flew through these clouds. That's the next step we can do. Another thing is we can like focus on the cloud top phase, like for example, like for the vertical structures of the LSR and the dipole. So the gray shadows here shows the estimated boundary boundary layer cloud boundaries, like cloud top and cloud base. The vertical profiles shows different, like when the dipole is relatively lower, and the LSR is relatively low. So this is a mixed phase case. But for the case on the right, we have a relatively lower depolarization, but a relatively large LSR, which means the supercritical liquid water, where the temperature, the cloud top temperature is very low, like below the -28 Celsius degree. So that's the general plans for the future research. The final acknowledgements. So thanks for the future co-authors for the research, and also thanks for our CAO discussion group, and as well as our earlier cloud physics group. That's the figures from Halloween last week. So here is a short update of my seminar and some preliminary results. So now I'm happy to take any questions about the CAESAR, about any figures. Thank you.
I'm happy to open questions to the room and online. So if you have any questions.
Sorry.
Please.
When they were doing the dropsondes, were they targeting for the cloud portions, or is it just, and could it be the upward or downward leg for doing the dropsondes?
Sorry, I need to stay closer.
Very good. So when they were doing the dropsondes, right, did they target just the cloud, so the upward portion of the rolls, or did they target both the downward and upward portion when they did those dropsondes?
They focus on not only the cloud, so that they release the cloud on the dropsonde every around 5 minutes.
Okay.
Yeah.
So they didn't have specific targets.
Yeah.
So I would wonder what it would look like if you were to segment out that initial analysis to what you could see in the downward leg versus the upward leg, and how that might be different, right? In those different dropsondes. So that might explain some of the wiggliness in some of your figures. Right?
Yeah, that's a very good point.
Yeah. So I'd be interested to see how that works. Since you do have the Doppler velocity, it should be relatively simple to do. Maybe. I don't know. It's hard to tell.
Yeah, I can try to look at it.
Yeah, just a suggestion. Because I know when they did stuff out in West Texas, terrestrial horizontal convective rolls, there were pretty significant differences in the downward versus up leg thermodynamic structure. It'd be interesting to see the same over the ocean.
Yeah. That's what we should. Thank you. Thank you so much for your suggestion. Yeah, please go ahead.
You in the first few slides have some time series of boundary height and also low level jet height. Yeah, in your case, the boundary height is about 2 kilometers.
Boundary height here, yeah.
2 kilometers. Then, so basically, you have very cold air above the warmer sea surface. So the turbulence is strong, so boundary height is high. In this case, you've got low level jets depths. It's 400 meters just in the middle of the boundary layer. That's kind of weird. Normally, in the convective boundary layer, they are well mixed, including the momentum. So we don't, just like daytime, we don't expect the low level jets in the middle of the convective boundary layer. Normally, low level jets is on the top of the stable boundary layer. So how do you define the low level jets in the convective boundary layer?
Yeah, that's a very good point here. Yeah, let me find out this. Yeah, like based I to find the low level jet based on this, like for the lower part of the atmosphere, finding the maximum of the wind speed as the low level jet core, and then finding the minimum the wind speed here. So the depth is between the minimum and the maximum. So that's the depth. And the strength is the maximum wind speed minus the minimum wind speed. That's the strength. So there are some discussions about how to define this. So here we have the low-level jet flag. So there are some arguments. Some people think like when they define the low-level jet strength, you have to make sure they have neither both of the absolute differences between the maximum and minimum. You also need to have the relatively differences, like which means you have the like 25% larger than the minimum, but both below and above. So there's some discussions, but some paper like recently published, like they said, oh, for the Arctic region, like we don't have to concern about the relatively 25% larger than the minimum. So I think that's the reason we have the weird, like one dropsonde have very higher low level jet strength for my figure, because I don't include the relatively 25% differences there. So if we conclude that limitation, probably these drops here will removed. So that will result like the other low level jet depths will be relatively lower. So probably will be the reason.
Yeah, if you go back to that
The definition.
profile that you were just showing.
Okay. Here.
Yeah, so, I mean, depending on what it is you're really trying to quantify here, the low level jet itself is actually below the zone that you're now quantifying as the depth, right? Because you've identified the nose, and now, you know, the depth is really, you know, kind of the area around that nose. And what you have above is just kind of your decreasing to free atmosphere, or whatever we want to call this, and only that down. Of course, in the Arctic, things are going to be a bit different, but there are a lot of definitions out there that, you know, include shear terms and things like this. I would definitely spend some more time thinking about how to define that. And, you know, you have these two noses that are very close to each other as well.
Yeah.
So, yeah, I would spend some more time thinking about that, because I agree, it was kind of interesting to see the kind of scale of the depth, thinking about what the scale of the boundary layer itself is or anything. So
yes, you try to find or identify low level jets with such convection there. Then low level jets is different from what we normally think about low level jets.
Yes.
Yeah, thank you. Yeah, that's a very good point. Yeah, I need to double check about it.
Yeah. We had a question online.
Yeah, sure.
From Michelle Swinzer. She asked about the method. How are you estimating boundary layer height? What method?
Oh yeah, that's a very good question too. Let me put out these. So I tried different ways. The first very common one is the d theta dp, the maximum gradient of the potential temperature over the pressure. Another two ways is use the Richardson number 0.5 and 0.25. So in most of the cases, like these three methods agree with each other very well. We can see like the overlap each other. And for some other cases, like when the d theta dp is over here, but the Richardson number we have relatively lower. So for this case, I just rely on the Richardson, rely on d theta dp. And for the method, for the cases on the right, the d theta dp here is relatively large, really higher here. But for the Richardson number, they're over here. But for this case, I also look at the dqdp, that's the specific humidity here, to see the maximum increment and decreasing of the dq here. So for this case, I will rely on the Richardson number. So for the 36 dropsondes, I just do these kind of choices based on these.
Any other questions? Okay, well, maybe we can thank our speaker. Thank you, Hazel.
Thank you.